So we're going to begin our first introduction to the Pybricks software by just doing a basic overview of some of the features and trying to compare it to some of the similarities between the Spike Prime Scratch software, so we can see where we are progressing from Scratch, and then understand how do we actually get to talk to things just like the way we would in Scratch, and what are the commands that we need to understand to be able to do that in Pybricks. So for First LEGO League specifically, we obviously are going to be driving our robot, and in Scratch we would actually tell the robot which motors are going to be used for driving. And in Pybricks it has something here in robotics which is called a drive base, and that drive base is exactly the same sort of feature that we would see in Scratch, where we're saying, hey, motors A and B, you need to be able to work together to be able to operate a pink block, for example. So if we want to drive forward using a pink block, those two motors need to join together to be able to do all of the stuff that's in the background of that block to make the motors drive together. This drive base, though, is a little bit more advanced, and it's incredibly powerful when we add in this part here. And we're going to change from, and this is the beta version of Pybricks, and it has another class in here which is called the gyro drive base. And I've just added the word gyro in there, no spaces. And what this drive base does is it actually uses feedback from the gyro to also inform how the drive base is working, which makes it, again, even more powerful. So, and we're going to see that in a second. So to be able to start off with, obviously we know that we are using a hub. This one here is actually a student's hub, and they've got one of the robot inventor kits, but it's the exact same features. Everything's pretty much the same in the way that we would operate it anyway. So all I'm going to do quickly is do a bit of a plan, and to do a plan I'm actually just going to add in some comments. So we've got here the hashtag symbol, and we can see there now that that's actually changed the color of the code. If I type in here normally it is black, but with the comment that we're adding here now, and this is what we're doing when we add a hashtag, that comment is now in green, and when the code actually runs on the hub, it won't see that. That is just there for us to understand. So there's a few things I need to know. I need to know, well, what is the left motor? Okay, what is the right motor? And if we're using, and it would be pretty standard on an FLL robot, there would be two accessory motors, or two motors that might run potential attachments or something else in there as well. So I'm just going to say here, maybe we could call it attach motor. Whoop, struggling. And we can call the attach motor 2, for example. And we're not using this within Coda, any code at the moment. What we're going to do is actually do some physical planning. So we need to know what port they plug into, because in Pybricks, this is one thing that we don't have, is an understanding of where some of those things are actually going. Without the heads-up display, we can't actually see up here where or which motors they are plugged into. So what I'm just going to do quickly is do some troubleshooting here. I'm just going to turn my robot on, and I'm just going to remove a little bit of Lego at the moment, / break some stuff. Alright, let's do some troubleshooting here. So this cord here is going down into one of the motors. So if I just show that quickly, it's coming into one of those little medium motors that's on the front. So I know that C is the left. Oh, that's just slid down. I'll just fix it up. C is the left attachment motor. So if we just call that, that's the first attachment motor. So I'm just going to leave that unplugged for now while I do this. I'm going to come back to my code. So this attachment motor here is actually in port C. Okay, so that's one of them. If I have a look here now, oh, okay, I've just unplugged this one and the color sensor went off. So I'm going to use, oh, it didn't come back on again. Let's have a quick look. if I unplug this side, let's take that bit off. Okay, so E and F both look like they are color sensors, so I'm going to leave them plugged out. And I didn't add them over here, so let's just add them again. Color sensor left was E, and color sensor right is port F. So if we go through and actually do a little bit of a plan here, from what I think the students have done when they've built this, C and D is the medium motors, A and B then must be the drive motors. But what we want to check is to make sure is this the left motor? So that cord's going down to the left there, so that would be the left motor. So the left motor is in A. I'm just going to bring this camera up here a little bit further. The left motor is in A, and that means the right motor then is in B. Okay, so let's plug some stuff back in. So this was a color sensor, and it went back into E. What's going on there? Okay, I might just tuck that back in like they had it. This is the large motor, which was in A. Just tuck that underneath there as well. GM it in there. And this one was one of the accessory motors. So I'll just plug in as well and put it back the way it was for the kids. Alright, so that's that side. On this side, we just need to plug the color sensor back in. But look at it. Alright, so if we turn the hub back on now, I'm just going to move all this extra Lego off to the side. We don't need that now. Let's just see if we can get it to do some of the things that we need to do. So, port C and port D was the other motor. The left motor was in port A, and the right motor was in port B. Okay, to use the motors, we need to make sure that we're addressing, and there's a thing up here that gets imported from a library, and we've got button, color, direction, port, side, and stop. So port is the one that we are going to use specifically, along with the one here that's come from some of the devices that can be attached to the brick. We've got a motor, a color sensor, and an ultrasonic sensor. So we're not going to be using the ultrasonic sensor on this build, but some people do. So I'm not going to import that. We do, however, need to use the motor and the color sensor. So let's go through the first set. So the first set I need to know is what is actually going to drive the robot. And we said that we've got left motor. And whenever I call on something, I'm going to make sure that it's all one word, because I can't do spaces in Python. So I'm going to use a underscore. So I've got an underscore there. So left underscore motor is equal to, and just like in Scratch we would say set movement motors to, this is exactly what we are doing now. So we are going to set our left motor, and we need to use the exact same syntax or the same type of font and size and everything else up here. So if I start to type it though, it will actually bring up all the different things, and the one we are chasing here is motor. So I'm just going to push on that motor, and then I'm going to do my brackets. Well, what port is it in? So it brings up an example here, and it says motor, and it says port, and it says I have to use a capital P. So port, and there it is. So I can just click on that now, and what it's going to ask me for now is what port is it in, and I'm just going to do a dot, and it's going to give me some choices. So it's A, B, C, and we know the left motor on this one, because we did this plan up here, is in A. Okay, and then we do a line down. Now we need to do the same thing for the right motor. So right underscore motor equals motor brackets port dot B. Okay, so the interesting thing now that we've got in here, and for people that haven't used the blue blocks within Scratch before, you wouldn't realize that actually when we're talking to the robot, if we spoke to just a motor by itself, sometimes the motor will go clockwise or anti-clockwise, and depending on which way the robot is traveling will depend on which way the motor needs to spin. So if I hold up this one here, and here is my motor, and if I find the exact starting point for it as well, so if I turn my motor around until I have my dark circle line up with my circle, if I turn it in a forward direction, my motor is going in a clockwise direction. Okay. If I do the same thing over here though, because the motor is actually mirrored, to drive forward, I am actually driving in an anti-clockwise method. So for it to travel forward, it's traveling the opposite of the other way. So this one is going this way, and this one is going the other way. Okay, so when we talk to them, and we talk to them in separate sentences here, because, well, we don't have the benefit of using the pink blocks, but we will later on. So what we need to do in this part where it says port B is we are actually going to find out now, well, which one is actually going to drive counterclockwise. So I'm going to say it's actually this first one here now, so it'll be the left motor, and I'm going to say it is. Well, we can see here it pops up with, well, is it in a positive direction, or is it in a direction that is clockwise or anti-clockwise? So ours isn't in a positive direction, ours is the opposite. So we're going to say direction, tab, dot, again, to talk to direction, and which one is it? Is it clockwise or counterclockwise? And I'm going to say ours is counterclockwise, so it's going in a different direction. And that's really important, because when we go to talk to these later on as a group, we need to let it know which way that it actually needs to turn to do what it's told. So from there, we have our two other motors. So we have our attachment motor, and I'm just going to call it well, let's just call it by its port number, maybe. Let's just say motor C, yeah, or motor D. So let's just say C underscore motor is equal to capital letter motor, and then we need to put it into the port. So we say port dot, and then this one was in C tab. Okay, it doesn't need anything special in there at the moment, so we will talk about accessory motors later on. D motor equals motor brackets port D. Okay, so they're all our motors done. And if we want to talk to color sensors later on, we can do that as well. I'm not going to focus on color sensors at the moment. I just want to do motors for the time being. So we've got our two motors that are going to work together, and our two motors that are going to be individuals for pretty much the entire time that they're operated. What we do need to do is come back to this one here where it says gyro drive base. So we're going to actually tell it what it is. So if we say gyro underscore drive underscore base is equal to the gyro, in which it came up before, that whole word, gyro drive base, which is the same as what we imported earlier up at the top. And what we're going to do now is we're going to call on a few things. And it says gyro drive base needs a left motor, a right motor, some measurements around what the wheel's diameter is, and what the axle track is of the robot. And I'll explain what that is in a second, but let's just focus on these first ones. It says here, well, it's actually already told us. Left motor is going to be what we set up here. It's going to be left motor. So I'm just going to type in here, left motor, tab, and now I'm going to do a little comma, and I need to give it, well, what is the right motor? So I'm going to type in right motor, and then the next thing is going to be wheel diameter, and it automatically pops up there. So I'm just going to hit tab to be able to let it work that out. So something that I'm using, and you'll notice a bit different here to some normal robots, I'm actually using the giant wheels. And the benefit of Pybricks over some of the other platforms, particularly Scratch, is that these these big wheels typically cause a lot of error. So they cause robots to be driving all over the shop, and they're really, really difficult to maintain a very tidy heading at the best of times, especially with turning. But with Pybricks, we've found that they are 100% reliable, and the added speed that we get from having bigger wheels is a big difference, and we'll see that in a second. So this wheel, if we got a ruler to be able to measure it, is 87. So if we come across in mils, and I start there, and we get an idea of where we're sitting, and it doesn't need to be spot on, but we can tune this later on if it's not exactly doing what we want it to do. So that's another benefit of being under these numbers. If we went into the Lego website and actually looked at the manufacturer of these, it would give us the exact figure of what that data is as well. So if we can't find it, or we're struggling to be able to find the measurement, which you shouldn't be, we should be able to do that by now, we can go to the website to be able to find out some of the data as well. So 87 is going to be our wheel diameter. The next thing is then axle track. So let's have a look at axle track. So if I type in axle, it then comes up with axle track. If I hit tab, it will move across for me. Okay, axle track. Let's have a look at this. If I flip the robot over, the axle track is the distance between the wheels and the one wheel and the other wheel. So if I come through, we can actually count this. So if I count in beams, so if I look at the pinhole for the beam, I can actually count. So we can go 1, 2 for this motor assembly part, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. Okay, so we've got 17 beams, and if we measure this and just make sure how we're going with this, so if we come from the inside, we're saying it's roughly 130. So 17 and what we'll notice is that if we go off what the difference between some of the beams themselves. So if you actually measure from one hole to the next, what we'll figure out is the beams are about 8 millimeters apart. So what we can do here is we can do 17 times 8, and we'll get that 137. And we said roughly it was about 130 when we measured it with the ruler, so that extra 3 mil is probably coming from the outside of the wheel. The interesting thing with these wheels is it's not the whole surface that actually touches the ground. That's the interesting thing when we start to tune this axle measurement, is we might need to change that a little bit. So let's just start off with what we know from 17 times 8, 136. And we'll start with that just to see how our robot responds to those numbers. So we've worked out the wheel diameter by not only measuring the wheel diameter, but also checking the measurements that are given to us from Lego. And we've also got the axle track using the idea of 8 millimeters between each of the little pinholes, and we can just count them across as we go to be able to figure that out too, which is easy enough to be able to do. What I want to be able to see now is if I address this robot and we connect to it. So let's connect to it now. So we've added all those things in. Go to Bluetooth and we pair this hub up. If we look back at the library software that's provided with this, and we have a look at how we can do some different things in here. So let's just come over here at the moment and have a look at the library. And I've got the library here. I'll just drag it out, and we can see that if I just go home, we can see all the Pybricks documentation. Here's all the hubs that we want to be able to talk to. So what we want to talk to though is the motors. And what we now have is we've got all the different ways we can talk to the motors. Let's go back though to this main one at the hub at the start here. If I come up to the 3 lines, there's actually some other things that we can go to. So I'm just going to minimize motors for the time being and minimize devices. I actually want to look in this one here where it says robotics and drive bases. So if I click on drive bases, it gives us that class, and we added down here as well. And if I just scooch down to the exemplar, it says this class here. So here's our gyro drive base, and it says this class just works just like the drive base. So if we wanted to, we can go back. We will need to make sure which type of which side the hub is mounted on. So if we've mounted the hub sideways, we will need to tell it which way is facing forwards. So the front side is the side that I've got now facing towards the front of my robot, obviously. So we need to know which side is actually working to be able to go through. If we look at the example that they give us down here, they've given us the same sort of thing to be able to set the left and right motor. They've also said drive base, which we've actually added in the gyro component of that. So it says gyro drive base. And this looks like it is something that, oh, there we go. So it's got 56 millimeters wheels, so it's using the small spike ones, and it's got an axle track of 112. If we look at what they've just said here, well, all they've had to do is tell the robot to drive straight 500, and the measurement above that says it's in millimeters. So we need to know some millimeters. So if I did a very basic calculation, and if I put my ruler just off to the side and I put the 0 there, pretty much on the space where the wheels are connecting now, what I want to see is if I can do the same thing. So let's just say we said gyro drive base, and there it is, it populates straight away. I'm just going to hit tab and away it goes, and we could say dot, and then it gives us some choices. So do we want to angle, distance, drive, heading, what else do we have? We want straight, so I'm just going to click on straight, and then in brackets, well, if I'm starting at 0, I just want to see, can it go to 300 and pretty much stop on the dot. So let's press 300 and let's press play. Wowzers, that is pretty much dead on. Okay, let's bring it back. Let's see if it can do it again. Yeah, let's say 250 this time. So I'm just going to change that 300 to a 250. Press play. Yep, spot on. Beautiful. Alright, so just by putting in the settings into the hub, we can see now that we have exactly what we wanted to try and achieve. So I'm just going to square this hub off with the wall. Might be a little bit deceptive with the camera angle. So other than straight, it's also got over here that we can just tell it to turn. And the turn that is interesting, which is probably going to surprise a lot of people because it's not possible on the EV3, well, not without a little bit of math going on. This is just simply typing in one command, is a turn to 180 degrees. So let's just see if this works. And that is perfectly straight. That does mean every time it does it. So let's try it again. Press play. It should come back around again. Beautiful. And again, whoop, kicking the sand. Again, perfect turn. So if we come back to, well, let's try a couple of turns. Let's try a turn to 180. And again, benefit of Python, I can just highlight the text I've got here. I can go Control C, enter down, Control V. And what I'm going to do is I'm going to do 2 turns. I might just add in a little wait here, and wait is in milliseconds. So if I put in here 1,000, it's actually going to be 1 second. So let's just see what it does. So I'm going to tell it to turn 180, wait, turn 180 again. Beautiful. Okay, so that is how easy it is to do driving and turns. So that is incredibly easy. So if we just did an example here again, I'm going to get it to drive roughly, let's just say 300 millimeters, and I'm going to get it to do a 180 turn and then drive back 300 millimeters and do another 180 turn, and hopefully it should be where we want it to be. So I'm going to space down here. I'm going to paste again. I don't want it to do a turn. I said I want it to go drive straight. So let's try it white straight, and I said 300 mil. I might give it a little bit of a weight. I want it to turn, wait, and then I want it to drive another 300. So if I just copy this down underneath my weight, paste it, copy another weight, paste it, we can see how quick it is to be able to do that code copying and sharing of it. So let's go through. We're driving forward 300 mil. We're waiting for a little bit. We're turning around to face the direction that we were facing again. We're driving back to where we were, and then we're turning around to hopefully be in the same position that we were from the start. So I'm going to make this really difficult for this robot here. I'm actually going to... I don't have a pencil on me here. Let's use a Lego beam. Let's just say this was exactly where the center point was. And let's just see what it can do. So I'm just going to put it off to the side a little bit. Let's press play. So there's a little bit of Lego under my bit of paper here. That's not good. But even with that there, that is perfectly straight. And as much as my Lego wasn't straight to start off with, it is pretty much dead on where it was to start off with. So let's be a little bit more picky. Let's come back to here. Doesn't help that our paper isn't level either, so I'm not being very kind to this robot, but it's good that it's still performing. So let's try it again. Let's press play. Exactly back where it started. So very, very accurate, and it does me in a few times where I've gone through and discussed this. It is incredibly powerful. What I want to be able to do now though is to, by default, the robot drives at 40 speed if we don't set anything. So what I'm going to come back up here and just show you quickly is this part here where it says settings. Okay, so what I'm going to do here now is to say gyro drive base dot and then settings, and in settings we can set different speeds. So I'm just going to put some brackets in here. 500 is roughly about the maximum that I would be using on the board. I don't think any faster than that's going to make it too much. The benefits won't outweigh the negatives with potentially doing some silly stuff of driving around a bit too fast. So if we think about the acceleration though, I want it to accelerate maybe a little bit slower. So I'm just going to put it at, say, 200. The next number is the turn. So if I come back up here and just read this, so it's got turn rate of the robot. So this again is just the speed. So how fast do I want the robot to turn? I'm going to let it see how it can go at a fast speed. So I'm going to say 500 as well. Now what I am going to change though is the acceleration at which it does that. So it automatically does both the acceleration and the deceleration of the robots by itself. So I can just put that in there. So you can do two different measurements here if you want to. So I'm just going to do 200 again. And let's just see, does this create a visible difference in our code? So if I adjust the settings here now and I press play, so the overall accuracy and everything else was there of the robot. It was probably a little bit slow. So let's see if we change that by 100, what does that do to the robot now? So this is again this tuning process and the idea of being able to constantly come back and make sure each individual part is correct before we just assume everything's fine and move forward. There we go. And back where it should be, perfectly in line again, and it is ready to go. So let's go through this again. Let's try for that straight drive. I might leave the turn a little bit less. That seemed a little bit better. Perfect. Beautiful. And again, back perfectly in line where it needed to be again. Awesome. So out of our first lesson, let's just recap. We've assigned our motors into the ports where they need to be. We've also assigned the additional motors that we have. We haven't spoken about them yet, but we will later on when we start to address some of those attachment motors. We've created our gyro drive my block, or what we would call there the overall gyro drive base, which is previously where we would have stored all of our settings and all of our parameters and everything else from our robot now, and it automatically does all of that calculation for us. We've tuned it a little bit here to be able to give it some probably more responsiveness in the straight drive and probably a little bit slower in the turns, which might be helpful later on when we start adding weight to it. What we've done is then been able to address this idea of straight and turn, and we probably won't do much more in FLL other than driving straight and turning, but something we will have to address and something we're going to have to think about is if we're just asking it to turn 180, it's not a absolute measurement, so we don't know where it was before that. So what we'd probably need to think about is creating some sort of comment along the side here of the cumulative turning. So if we said here we were driving straight, that would be, if I do a comment here, and we would just say that was 0 for the heading as it was. The heading is now, as it's turned, we would put another comment in here and we'd say it's now turned to 180, and now it is actually driving forward at 180. Okay, so this would be our cumulative heading here. If we turn to 180 again now, well, what is it actually going to be facing? Well, that's 360. So it's now done a 360 degree turn as it goes through. But if we started at that and we've turned 180 here, we've driven at 180 and we turn back again, we've just turned right turns. So we're actually back at 0 again. And this is something I would really encourage the students to understand as they go, because they need to know their global position. They need to know where their robot is, and that should be easy to follow through the code. So whatever system you come up with for this, I think that would be super helpful for students to be able to understand, knowing that 0 is the absolute heading of where it started that particular code. So it'd be good for them to understand if they're coming back to a position and that is 0, well, then that is where they actually started. Okay, so I'll end it there. This will be the first lesson that we go through, and then from there we'll start to go into looking at some of these attachment motors, and then we'll work into understanding some of the color sensors and some of the other stuff associated with the robot as well. Well done.